In Chapter 6, Section 4, we will cover the central limit theorem. The central limit theorem states that the sampling distribution of the sample means approaches a normal distribution as the sample size gets larger, no matter what the shape of the population distribution. This fact holds true especially for sample sizes of over 30. All this is saying is that as you take more samples, especially large samples, your graph of the sample means will look more like a normal distribution. In this section, we are introduced to and we will apply the central limit theorem. The central limit theorem allows us to use a normal distribution for some very meaningful and important applications. The central limit theorem states that for all samples of the same size n, with n greater than 30, the sampling distribution of x bar can be approximated by a normal distribution with a mean mu and a standard deviation of sigma divided by the square root of n. The following are two key points that form the foundation of estimating population parameters and hypothesis testing. They are that with the central limit theorem and sampling distribution x bar, it is given that first, population with any distribution has a mean mu and a standard deviation of sigma, and second, the simple random samples all of size n are selected from the population. The practical rules for real applications involving the sample mean x bar include the following. There is a requirement that the population has a normal distribution or the sample size is greater than 30. The mean of all the values of x bar is equal to mu of x bar is equal to the population mean mu. The standard deviation of all of x bar is sigma of x bar is equal to sigma divided by the square root of n, or the sample size n. And also the z-score conversion of x bar is equal to z-score equals to x bar minus mu divided by sigma over the square root of n. Also, under the practical rules for real applications involving a sample mean x bar, we can say that if the original population is not normally distributed and the sample size is less than or equal to 30, then the distribution of x bar cannot be approximated very well by a normal distribution, and the methods of this section do not apply. So when we're working with a sample, we want to check some requirements. First, when working with a mean from a sample, verify that the normal distribution can be used by confirming that the original population has a normal distribution or that our sample size is greater than 30. And second, we want to determine if we're using an individual value or a mean from a sample. We want to determine whether we are using a normal distribution with a single value of x or the mean x bar from a sample of size n. When working with individual values from a normally distributed population, we can use z equals to x bar minus mu over sigma. When we are working with a mean for some sample of n values, we can use the value of sigma over the square root of n for the standard deviation of the sample means. So in that case, we will use z equals to x bar minus mu over sigma divided by the square root of n. Let's review some notation for the sampling distribution of X bar. If all possible simple random samples of size n are selected from a population with a mean of mu and a standard deviation of sigma, the mean of all sample means is denoted by mu of X bar, and the standard deviation of all sample means is denoted by sigma of X bar. And so we would say that the mean of all values of X bar is mu of X bar is equal to the population mean mu. And we'd also say the standard deviation of all values of X bar is sigma of X bar is equal to sigma divided by the square root of n. Note that sigma of X bar is also called the standard error of the mean and is sometimes referred to as the SEM. Let's consider this example of safe loading elevators. The elevator in the car rental building at the San Francisco International Airport has a placard stating that the maximum capacity is 4,000 pounds or 27 passengers. This converts to a mean passenger weight of 148 pounds when the elevator is full. We will assume a worst-case scenario in which the elevator is filled with 27 adult males. Assume that adult males have weights that are normally distributed with a mean of 189 pounds and a standard deviation of 39 pounds. First, let's find the probability that one randomly selected adult male has a weight greater than 148 pounds. And then second, let's find the probability that a sample of 27 randomly selected adult males has a mean weight greater than 148 pounds. Let's solve for part A. We'll use the methods presented in a previous section because we are dealing with an individual value from a normally distributed population. We want to find the area of the green shaded region of our graph shown here. If we are using table A2 in the back of our book, we can convert the weight of 148 pounds to a corresponding z-score. So we do this by using our z-score formula of 148 minus 189 divided by 39, and that equals to negative 1.05. So when we refer to table A2 to find the cumulative area to the left of our z-score of negative 1.05, we find that area to be 0.1469. So the green shaded area to the right of our z-score would be equal to 1 minus 0.1469, which is equal to 0.8531. And so we can say that the probability of randomly selecting an adult male who weighs more than 148 pounds is 0.8531. Recall for part B, we want to find the probability that a sample of 27 randomly selected adult males has a mean weight greater than 148 pounds. We can use the normal distribution if the original population is normally distributed or we have a sample of greater than 30. The sample size in this example is not greater than 30, but recall that it was stated that the original population of weights of males has a normal distribution. So sample sizes of any size will yield means that are normally distributed. Because we are now dealing with the distribution of sample means, we must use the parameters mu of x and sigma of x, which are evaluated as follows. Mu of x is equal to the population mean, which is equal to 189 pounds, and sigma of x is equal to sigma divided by the square root of n, which is equal to 39 divided by the square root of 27, and that equals to 7.51. So since we want to find the probability that a sample of 27 randomly selected adult males have a mean weight of 148 pounds, we will want to find the green shaded area shown in this figure. Using table A2, we can convert the value of x bar equals to 148 to the corresponding z-score of z equals to negative 5.46. The equation here shows us how to get that corresponding z-score of negative 5.46. And then from the table, we find the cumulative area to the left of our z-score equal to negative 5.46. And that area is equal to 0.0001. So the green shaded area to the left of our z-score is 0.0001. And then the area to the right of our z-score would equal to 1 minus 0.0001, or 0.9999. From this, we can state that we're quite certain that 27 randomly selected adult males will have a mean weight greater than 148 pounds. So we can interpret our results as follows. There is a 0.8534 probability that an individual male will weigh more than 148 pounds. And there is a 0.9999 probability that 27 randomly selected males will have a mean weight of more than 148 pounds. Given that the safe capacity of the elevator is 4,000 pounds, it is almost certain that the passengers of the elevator will be overweight if it is filled with 27 randomly selected males. This example shows that we can use the same basic procedures from section 6.2, but we must remember to correctly adjust the standard deviation when working with a sample mean instead of an individual sample value. The calculations used in this example are exactly the same type of calculations used by engineers when they designed ski lifts, escalators, airplanes, boats, amusement park rides, and other devices that carry people. In Chapter 8, we will use the underlying assumption that all inferential statistics deal with rare events, and that's why probability is used so extensively. The rare event rule for inferential statistics states if, under a given assumption, the probability of a particular observed event is very small and the observed event occurs significantly less than or significantly greater than what we typically expect with that assumption, we conclude that the assumption is probably not correct. In other words, the rare events rule states that if an assumption is made and the probability of a certain observed event is very small, then the assumption is most likely incorrect. Let's consider this example. Assume that the population of human body temperatures has a mean of 98.6 degrees Fahrenheit, and also assume that the population standard deviation is 0.62 degrees Fahrenheit. If a sample size of n equals to 106 is randomly selected, then find the probability of getting a mean temperature of 98.2 degrees Fahrenheit or lower. We are working under the assumption that the population of human body temperatures has a mean of 98.6 degrees Fahrenheit. We weren't given the distribution of the population, but because the sample size exceeds 30, we can use the central limit theorem and conclude that the distribution of sample means is a normal distribution with these parameters, where the mu of x bar is equal to the mu, the population mean, is equal to 98.6, and sigma of x bar is equal to sigma divided by the square root of n, and that's equal to 0.62 divided by the square root of 106, which is equal to 0.0602197. This figure shows the shaded area to the very, very far left tail of the graph, and that corresponds to the probability that we are interested in. Having already found the parameters that apply to the distribution, we can now find the shaded area by using the same procedures as developed previously. If we use table A2 to find the shaded area in our figure, we must first convert our value of x equal to 98.2 to the corresponding z-score. And that z-score is equal to 98.2 minus 98.6 divided by 0.0602197, which is equal to negative 6.64. Referring to table A2, we find that z equal to negative 6.64 is off the chart. But we know that for values of z below negative 3.49, we can use an area of 0.0001 for the cumulative area left of the z-score. Therefore, we can conclude that the shaded region is 0.0001. Our results can be interpreted as follows. The results show that if the mean of our body temperatures is really 98.6 degrees, then there's an extremely small probability of getting a sample mean of 98.2 degrees or lower when 106 subjects are randomly selected. The University of Maryland researchers did obtain such a sample mean, and after confirming that the sample is sound, there were two feasible explanations. First, the population mean really is 98.6, and their sample represented a chance event that was extremely rare. Or second, the population mean is actually lower than the assumed value of 98.6 degrees Fahrenheit, and so their sample might be typical. Because the probability is so low, it's more reasonable to conclude that the population mean is lower than 98.6 degrees Fahrenheit. In reality, it appears that the true mean body temperature is closer to 98.2 degrees Fahrenheit. In applying the central limit theorem, our use of sigma of x bar equal to sigma over the square root of n assumes that the population has infinitely many members. When sampling with replacement, the population is effectively an infinite size. When sampling without replacement from a finite population, we may need to adjust our sigma of x bar. A common rule for that adjustment is when sampling without replacement and the sample size n is greater than 5% of the finite population size, capital N, we adjust the standard deviation of the sample means sigma of x bar by multiplying it by the finite population correction factor of the square root of capital N minus lowercase n divided by capital N minus 1.